My name is Richard Heyns. I'm the founder and CEO of a company called Brytlyt. And I'm going to be talking along with Jakob, who's our head of R&D, about some of our experiences with porting to Power. A lot of the presentation is based on our experience with Power 8, and recently we've updated that to Power 9 as well. And very much focused on getting the most out of the GPU side of things, and of course NVLink, an NVLink between the host and the device. So the company is called Brytlyt. I'm going to give you a little spiel about the company to start off, a bit of an intro. And we're using graphics processor units to massively accelerate data processing and deliver speed of thought analytics at scale. Brytlyt is a Postgres clone. So from a user perspective, you're interacting with a Postgres tool, but everything in the background has been developed to run on graphics processor units. So you get that massive improvement in performance. And there's a couple other tricks in our bag related to AI as well. But if we could just take a step back for a moment. Bob Dylan talked about times are changing, and that was a while ago. And I think the context of that comment was maybe a bit deeper, but times are changing, things are moving forwards, and the data that we have available and the hardware and technology that we have available to us today is like nothing before, and that is moving on massively. That's a Falcon heavy lift rocket taking off. I think it's an awesome photo, but really that symbolizes the kind of hardware platforms that we have available to us today. Fantastic hardware, that Falcon 9 rocket, the heavy lift, the biggest rocket in operation today. And the analogy to that is the IBM Power 9 hardware platform that's designed to connect GPUs directly to the motherboard using NVLink. So fantastic hardware and compute resources available to us today. A little bit about how that plays into what Brytlyt can do. We're a GPU accelerated database, and it delivers a new paradigm in time to value for users. The two graphics there, the two graphs, are performance and memory bandwidth. The orange lines are GPU compared to CPU performance over time. And the two really interesting characteristics there is, one, GPUs are incredibly more capable devices than CPUs, and that gap is widening over time. So in the next 2 to 3 years, GPUs for certain data processing workloads are going to totally dominate what is possible and will be the hardware platform for choice, leaving GPU databases at the pinnacle in the evolution of database technologies. Differentiators for Brytlyt. So our mission statement, shall I say, is to empower organizations through transformational data analytics and to deliver speed of thought at scale. And we do that by being the recognized world leader, the fastest database from independent benchmarking. We've spent over 4 years in research and development, perfecting the product. We're the only vendor to have patent pending intellectual property, and our 4th generation GPU manager bridges the gap between artificial intelligence and SQL. The true value of what Brytlyt can deliver is not just the performance or being able to run on GPU, it's actually how that performance is packaged up and how we present that capability to our users. This is just a publicly available benchmark done by Mark Litvinchik. Pretty straightforward benchmark, but it's a standard benchmark. So 1.1 billion rows of taxi data, 4 queries, pretty standard aggregational type queries. And he's run that on a range of different technologies and hardware platforms. I've just selected out there 2. Right at the top is Brytlyt, and right at the top of that is Brytlyt running on IBM Minsky, which was the Power 8 platform, 5 nodes, 4 GPUs each, 20 GPUs. and compare that to an 11 node AWS cluster running Spark. Those times are in seconds. So for that first query, we were returning an answer in 5 milliseconds on 1.1 billion rows of data. Spark was taking 10 seconds to return an equivalent result. So just transformational, between 600 and 1,200 times faster than Spark. And this means that queries that might run in 5 hours can now run in under a minute. And even queries that might have run 10 hours on that Spark platform can now run in under a minute. So transformational experience for analysts that are using these kinds of platforms and processing this kind of data. There are a range of vendors who are offering GPU acceleration. Brytlyt is one of them. Scream's in the room as well. Kinetica is in, I'm not sure if Kinetica is here. Anybody from Kinetica? No, okay. So, and different vendors are taking a different approach to this GPU capability. Brytlyt is looking at very much a GPU-centric. We get the data onto the GPUs and use it exclusively there. That means we can really tap into that power, and we can deliver 4 terabytes a second performance. Kinetica are very much focused on keeping data on CPU and shifting it onto GPU, which means that they are limited by CPU RAM, and that has an impact on performance. And Scream, from the benchmarks that I've seen, transferring data from disk to GPU, and so some of those performance characteristics are related to the constraints around getting data off disk. So what that delivers, extreme performance that is enterprise ready, real-time performance that is packaged up in Postgres. So all the good things that you can imagine that you get out of Postgres, easy integration, existing code, existing investments in SQL code, dashboards, stuff that you might be doing on Tableau and so on, are all capable and will work out the box with Brytlyt. Some features and benefits with the product. So the full integration with Postgres, so we can take on a range of SQL workloads. Very tight integration with PyTorch, so we can also take on AI workloads. And this tight integration is actually fundamental to the architecture. So if you think about what PyTorch is, who's familiar with PyTorch here? Okay, 1, 2, 3, 4. Okay, so PyTorch is one of the AI frameworks like Google TensorFlow, Theano, Caffe, those kinds of things. And these AI frameworks basically work with tensors. So that's the kind of data structure that they consume. It's in the name Google TensorFlow, so there's the tensor in the actual name of the product. But a tensor essentially looks like a list of data, very much like you would see a list of data in a column of a database. And so we actually use tensors for the columns in our tables in our Postgres database. And we also use tensors for the machine learning and AI workloads. And actually, those tensors are all PyTorch tensors. So we've taken PyTorch, the memory management module within it, extended it and enhanced it, tied it into our Postgres capability. And so you can run SQL workloads on GPU using Postgres, and then immediately start running PyTorch workloads on the data in those columns without needing to copy it out of the columns even. So PyTorch, believes that those columns are actually its own tensors. So that's the introduction of the product. I've got a question over there. Jakob's about to come up, but let me just answer that question. Sorry, could you repeat the question? I couldn't quite hear what you're saying there. Okay, let me pick that one up first. So when we say zero copy, we literally mean zero copy. So when we declare a memory space to store data in a column for the database, for a Postgres table, we will declare a column of data, basically an array or a vector or a tensor, whatever you like. We can then flip a pointer, and that column can be consumed directly into PyTorch code, as if it was a PyTorch tensor. So you're literally reading the data directly from the column in the database on GPU into your PyTorch model. That you're not copying it out of the column across NVLink or PCIe, or you're not even copying it onto another column on the GPU. There is no copy. It directly reads it out of the column into the PyTorch machine. Okay, that's probably a bit more technical than I can handle, so I'll leave that to Jakob. So was there a question over here? Yes, sir. Correct, yes, that's right. Exactly right. Exactly right. That's right. So that's our. Let me just get onto that slide. This one over here. So when we talk about being able to read 4 terabytes a second, that's on a single Minsky or Power 9 machine with 4 GPUs. Each of those GPUs can read data at 1 terabyte a second. So that's how we get that sort of throughput. And you would then stack those up. If you needed a larger data set, then you would stack those machines up. So when we did our benchmark for the billion row data set, we had 5 machines, 4 GPUs each. That gave us the memory footprint. Theoretically, as far as terabytes. So each GPU has its own process managing it and is addressed by an IP and a port. And we have a controller, a hub, that knows about all the GPUs that are in its cluster and how data has been distributed onto them. So that hub then sends commands to the GPUs for push-down processing, aggregation, sorting, filtering, push-down joins, all happen on the GPUs, and the result is... So this is an analytic database. Yeah. Does that make sense? Cool. Cool. Okay. I'm going to hand over to Jakob. Oh, okay. Right.
Okay. Hello. Okay. So hello everybody. My name is Jakub. I am a head of research in Brytlyt. Maybe I start to try to answer the question about unified memory and possibly managed memory. So actually, we don't need to use unified memory because we store data in a GPU memory. We are focusing only to having data persistent on a GPU. But in a new version of our application, we will also have a mechanism of asymmetric columns. So we will be able to keep a part of a column on in a CPU RAM and the rest of a column in GPU RAM. But to swap the parts of memory, we have our own indexing like mechanism using accelerated structures. So with unified memory, the way how unified memory swap memory pages is implemented by NVIDIA and based on some heuristics. And because we are a database, user know what exactly he will be sorting on and how he is going to do operation. He can send up indexes. So we have our own acceleration structure to manage memory transfer. But at this moment, we are strictly GPU memory based product. Yes. Okay. So I'm going to tell a few words how we moved and how our pipeline for compiling for Power 8 and Power 9 looks like. So last year we did a benchmarks for Power 8. Recently we received an access to Power 9 machines. In general, it should be quite easy and straightforward process, but it's sometimes it was a little bit bumpy road. So maybe I start talking about how we did it. So basically, because at the beginning we didn't know and usually the application creators does not know the vendor of a hardware. It's better to build software in our own system. So we need to do a cross compilation to be able to compile on x64 machines for Power machines. So to do that, we need to set up the environment. We decided to set up the environment within the Docker x64 Docker image because it's an easy way to prepare a whole setup for building application and keep it on Docker Hub, and all developers in our company has access to prepared working environment. So we just started from a standard NVIDIA image in NVIDIA Docker repository, we installed cross-build tools in that. And this was the beginning of some problems, not the hard ones, but the standard. We had the problems with installation of packages, libraries required for our application in to cross-platform build using standard apt repositories. So in theory, this syntax here, apt-get install package architecture should work, but it didn't. So mainly we had to install the libraries in target machines and just copy libraries and binaries into our folders, in our x64 image. And the same situation was about CUDA libraries when we had to have compiled libraries for linker within this image. So we also just copied that from our target machine. Also, there was some work which we had to do with our CMake files. So our application is based on CMake, which is very convenient for us. So here's a list of flags and which we had to add to our build system. It's quite easy to forget about one and have also some problems with additional problems with compilation, but in general, this list here is a recipe how it can be done quite easily. So as you can see, it's a build for SM70 and compilers and also libraries for CUDA for Power. These are the libraries which we just copied from a target machine into the targets folder and subfolder of PPC64LE. So, okay, so our deployment looks like that. We have 64 image. We built a binaries here. We have also in a repository an Docker image for Power 8, Power 9. We keep that image. It can happen during our night build, so this is automated part, and during our night builds, the prepared image can be deployed to Docker Hub and next downloaded to Power 8 or Power 9 servers. Yes, but so it was a nice start. We have our binaries built and everything prepared, but it was impossible for us to achieve that transfer which they promised to us. Actually, when we looked at the memory bandwidth, it was very similar to PCIe transfers. So with Power 8, so what actually happened? So the next part will be a little bit about NUMA architecture. So as you obviously know, with Power 8 and Power 9 system, we have 2 NUMA nodes. And to each processor there is an NVLink connection with NVIDIA GPUs, V100 in case of Power 9. And also, this is a diagram of Power 8 machine which we used for our benchmarks, which Richard presented. So also to each memory is connected also to each NUMA node. And it was, and the problem which happens when we looked at the logs in a visual profiler, we didn't have a situation when something was serialized. It looked like everything was, memory transfer was happening in parallel, but two transfers we can observe were super quick with a bandwidth which we expected, and for two others GPU were super long. And with a first look, we didn't know why it's happening, and obviously what happened was that we allocate memory on host in a memory assigned to one NUMA node, and we tried to do a host-to-device copy to a GPU connected to second NUMA node. So okay, we identified that problem by using visual profiler, but so in theory using NUMA SDK should be quite easy to fix it, but it also wasn't. So yes, you have basically, it's not a output from a power machine, it's a standard 2 NUMA nodes machine, so you can check the nodes, how many NUMA nodes and then numbers of NUMA nodes using just ls CPU flag. So this is a standard server with 2 NUMA nodes, x64 architecture, and this is how the output looks like. And you can control the assignment of a process. Actually, not control it. This API gives you only a hint how you can provide you a possibility to give a hint on which NUMA node your program will be executed, your process will be executed, and where you will actually allocate your memory. There are two ways to do that. One way is you can control that process from a higher level, from a level of operating system. So you can just use a NUMA control command, and I will show an example later how to use it. So you can bind a process to a certain to a NUMA node, and also try to allocate memory in a RAM connected to NUMA node. And this is, as Richard mentioned, our application is cloud-based, so we can. So the first approach, which worked quite good, was not to modify the code of application, but just we created two separate nodes on one machine. So we ran two instances of our application on a single machine, and we just use that. So this is our application called GPU Manager. This is a process which is responsible for computing in our database, and we just use NUMA control methods with binding CPU and memory to a single NUMA node, and we started the process. And so instead of having one process controlling all GPUs, we just created two processes of our application. Its application is distributed, so these two processes can communicate with a hub. So it actually doesn't matter a lot if you have two processes running or a single one with management inside a code. So this is one approach how you can deal with that problem. And the second possibility is to use application level NUMA management. So there is also a NUMA library and set of functions which you can use inside your code to do that assignment. So, okay, so maybe, and it was also not such easy as we thought, because there was a kind of magic in that certain combination of these functions from this NUMA API did work correctly. Some other combination which should do exactly the same things didn't work, and actually we didn't know why. So I can present you a quick example how we can allocate memory, do a transfer, and do computation using that architecture. So to do that, I use just a function run lambda by thread. It's not a super complicated function. It just running lambda by thread using standard thread library. Okay, so to do allocation, we just first need to allocate memory on host. To do that, we use a NUMA run on node and standard default one allocation of memory with new operator. And this is first thing you can find in documentation that there is a function NUMA alloc on node, which in theory should allocate memory for you on a node which you choose. But unfortunately, we found that it was work on other architectures. Here we had a problem that with that line of code, nothing was happening actually, but with just NUMA run on node inside a thread and standard allocation, it started working as we expected. And we checked by a NUMA hits utility that it had been correctly executed. Second thing is host to device transfer. And again, by looking at NVIDIA documentation, you can in theory find a solution with streams. So to do asynchronous memory allocation and transfer, in theory, you should create a streams, add some flags to compiler, use that streams, use memory allocation, and CUDA memcopy async. So we did it exactly as it was on NVIDIA blog. But unfortunately, again, when we look at Visual Profiler, it looked like a serial execution. So we had a memory transfer one after one after one. Yes, and we started playing with that a little bit more. So the solution proposed on NVIDIA blog was not without using threads, just additional flag to compiler, memory async copies and streams, but it didn't work in this case. The solution which worked correctly was again to set up a NUMA node. We didn't need to create separate context within the thread, what was also suggested on some forums and in some tutorials. But NUMA run on node was enough, and CUDA set device and just CUDA malloc to allocate memory, and so this is a standard way, but with a selected node. And this is a copy part. So we didn't manually create it as streams, but we use default streams, and also inside the run lambda by threads function, we called a mem copy async. And it was a successful solution. We achieved this transfer which we expected. So in total, it was 120 gigs per second. So this is a report from Power 9. You can easily check your transfer by just so the easiest way to for us to use Visual Profiler, everything was Dockerized on external servers. So the easiest way for us was just to generate the output file of Visual Profiler with that command and download that file, and next in your local machine you can open that file in a Visual Profiler. And the transfers which we get was a total parallel transfer of 30. I think something is wrong.
31,000.
Yeah, yes, it's 31 gigs. Yes, 31 gigs per card, and yes, it was Power 8, and it was full parallel transfer. So in total, we achieved what they promised us. So about 124 gigs per second. And yesterday, so it's not included in this presentation, but yesterday we made the same test on Power 9, and we achieved a parallel transfer of 70 gigs per second per card. So 280 in total. So quite nice results, I think. Okay, and I think this is all what I wanted to say about memory transfer and how to achieve promised results. So, Richard?
Any tech questions for Jakub?
Thank
Thanks, Jakob. So, oh, there we go.
Okay, so for us it's important to be able to load data to database quickly to do some aggregation. So host to device is more important because we need to load data at the beginning of a setup to a RAM memory, and next quickly transfer the data to GPU, do some computations, and usually output of this computation is a couple of numbers, results of aggregation. So results were or worse for a device to host. It was in Power 9 it's about 40 instead of 70, but it wasn't very important from a point of view of our application. Yeah. Yeah. Okay. 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 I will. Okay. Interesting. I will look at it. Thank you.
Okay, so that's how we achieved full bandwidth or close to full bandwidth on NVLink from the motherboard to the GPUs to the hosts, and realized the fantastic potential that we have with Power 9. Just a little bit about how that then ties into the product itself. So Brytlyt is a Postgres clone. We've done a lot of work rewriting the database engine to actually run commands via our GPU manager. The GPU manager controls the GPUs, and we actually have a dedicated GPU manager for each collection of GPUs. So in the example that Jakob was talking about, there were 2 GPU managers on a single Power 9 server, and you might have 5 servers. So you'd have 10 GPU managers, and they all interact with each other using IP. GPU manager controls the GPUs. But from the user perspective, everything is Postgres. So they interact with Postgres tools. All the third-party tools and pieces of software that are out there will work. So, for instance, Tableau has a Postgres connector as standard, and you use that to connect to a Brytlyt database. We use pgadmin as our command console, and we use PSQL for our command line. So all of those things work out the box. Things like stored procedures, all of the Postgres PGSQL works. Cursors, JSON, user-defined functions. We use a lot of user-defined functions ourselves. Foreign data wrappers is also something that's really cool with Postgres. It makes it very easy to connect to existing data sources with a single line of code. You can present them on the platform as a table, and you can start running SQL and extracting data from existing data sources. So how does the whole stack sit together? In the middle, you've got Brytlyt software, the Brytlyt API, basically the GPU manager, and that can scale out. In blue, you've got all the tools that you can use to connect to the database with, starting with Postgres, so full-blown everything you need from an SQL perspective with Postgres. On the right-hand side, all the visualization tools, Tableau, MicroStrategy, Power BI, they all come with Postgres connectors. So they will work out the box, except they will work 1,000 times faster. We also developed our own visualization capability as well, because for 2 reasons. One is products like Tableau do have some overheads, and even when you hook them up to very fast databases, Tableau slows things down. So we've got our visualization tool that gets around some of those overheads. But even more importantly, very few visualization tools today can actually cope with large amounts of geospatial data. And that's because they're designed to run the rendering on client. So for Tableau, all the images you see are actually rendered from data that comes and lands on the client. And if you've got a billion rows of geospatial data, to start mapping those points onto a map, it's just not going to work, because it would have to all be done on the client. And then there's Torch, PyTorch, and Jupyter tight integration, which gives us this zero copy between SQL workloads and AI workloads. At the bottom, very easy to get data into the platform using foreign data wrappers, as I mentioned a little bit earlier. Postgres is an open source database. There are something like 60 foreign data wrappers in the community today, and so pretty much every single data source that is out there has a foreign data wrapper that you can then connect to directly from Brytlyt to start getting data into the platform. Two main products. There's the database, which is a Postgres clone. So from a user perspective, it looks like Postgres and acts like Postgres, except it's much, much faster, running on GPU. And then Spotlight, which is our analytics workbench, tight integration with PyTorch, so you can combine SQL and AI workloads. Very tight integration with Jupyter, so you can, using a browser front end, do all your visual analytics, so your charting, your geospatial analytics, SQL editor, full-blown SQL editor. You can do all your DML, DDL, write store procedures, user-defined functions in that SQL editor. And this is all within a browser. Single sign-in. You've got tight integration with Jupyter, so you can write all your Python, PyTorch code. And we also have a tool for task orchestration and creating data pipelines. So you can connect up tasks, hook them up in any combination, and start to build ETL pipelines, data enrichment pipelines, machine learning pipelines, all of which is running SQL or PyTorch, but everything's happening on GPU very, very efficiently. So that is the end of the presentation. Hope it was useful. Any questions, comments? Yes, sir. What you do is, I hope you don't mind me taking that, Jakob, as an answer. So let's jump onto that. So actually, let's go into the architecture. So when you create a table, create table statement, you either create a normal Postgres table, and then it's that data goes into disk, and you would use it as a Postgres table. Or you say, I'm going to create a GPU table. And the memory gets allocated, the columns get allocated, space gets allocated, and the data gets piped onto GPU. So you create the space, and the data goes onto raw data onto GPU. There are some elements where we compress the data. So there are columns that we have different compression methods, just for space and performance. But otherwise, the raw data goes onto the GPUs. You then send a query, whatever those queries are. Might be an aggregation, might be aggregation and a group by, a filter, and a join with some expressions. So yeah, absolutely. Yes, yes. Yeah. Yep. I think I got the question. So the question is, so there's a bunch of things that you're asking. Well, some of them are technical issues around GPU GPU footprint, memory footprint, architecture, how you can bring as much GPU RAM into play, and then also, how big a data sets you're working with. And that's a philosophical question that I'm going to answer, leave to the end. But the first thing is, so GPUs today can get 32 gig, okay. Power 9 has got 4, sometimes 6 GPUs. The Power 9 architecture has NVLink to the motherboard, which no other architecture has, which means that you can actually, in a modular way, stack those servers up, and we can bring 10 Power 9 servers into play, each with 128 gig of GPU RAM. So 10 servers are going to give you 1.2 terabytes of GPU RAM. But if you look at some of the other platforms that are on the market today, NVIDIA have released GDX2. It's got 16 GPUs, each with 32 gig of RAM. That's half a terabyte of GPU RAM for a single machine. Okay, so and it's about 300K, right? So it's quite an expensive machine, right? So it's not cheap. But that's where we are today. AI, machine learning, is driving a huge investment from NVIDIA. So that's not the start. That's not the 2 or 3 years time. That's going to double again. And the same comment was made about in-memory databases 5 years ago. Who would have thought that you put the whole database into in-memory? But people do that in some circumstances. There's a gaming company in the UK, King, who do Candy Crush and so on. They've got a huge investment in in-memory databases with something like a 10 or 20 terabyte in-memory solution. And when you look at some of the Spark installations, those are also in the terabytes. So one can definitely start to see GPUs moving in that way as well. The other thing is, yes, there are instances where the cost is just too great, and one wants to then dial back and maybe lean on CPU RAM, and absolutely our architectures can then cope with that. But obviously there's then a performance compromise because you're starting to make greater use of slower hardware. But the other thing is, I think, the philosophical side of things and data is we've been almost spoilt by how Hadoop, with the advent of Hadoop, where it was actually very cheap to gather and store huge amounts of data. And really the whole selling of Hadoop has relied on us gathering and storing huge amounts of data. But if you look at data and you look at its value, and you look at relevance and timeliness, there's a small section of really high value data that's relevant and timely, and then a huge tail of redundant data. Who cares what weblogs were shoving out 2 years ago? What we're really interested in, say from a retail perspective, is what our customers were doing yesterday and today, or what our weblogs are doing right now. And that's a much smaller segment of information, but far higher value. So what we...
This is for real-time reporting. If you look into data science for trending, and do not work with, a very small set of data. You need to take a look at a year, 2 years, 5 years to really get the good insights. I completely agree that if you need to know what was done yesterday, you need a very small piece of the data. Maybe you can then move it into a GPU environment with the memory, whatever, and run things in milliseconds and really make very fast decisions. You see the idea behind it.
Mm-hmm. Yes, sir.
Let's talk about real problems. We had a small
Yes, that's right. Yeah.
where you store your database in a different format, in a column-oriented format, in a file system. And
Well, not in a file system, because it's all on GPU. So if you turn the machine off, then you got to reload from.
Okay, the persistent data is important because you have a project right now runtime. But once it's copied to GPU for processing, you need to have it in column format.
that means your basic persistent data is row-oriented.
Yes.
And you copy the data column per column into the GPU, and you store it in column-oriented.
Yes, exactly. Plus some additional mechanisms for this done in CPU memory, flash format for RAM memory and also the disk memory, so to be able to reload it quickly
For instance, if you compare it to the solution stream, they store the data in column-oriented format on disk. They don't need to convert it into a GPU form. And that's why they are able to process petabyte databases. But the restrictions of MAPT or of your solution is that the database couldn't be very big.
Yeah, no, I agree with that. There's different use cases and approaches, and I think absolutely Scream has taken a very different technical approach to the solution, and that means that the use cases that they look at are very different. So we're not looking at petabyte databases, definitely not. That's not what we're. So I would say up to 10, 20 terabytes. It does depend a little bit on the budget of the customer. But some of the banks have 40,000 GPUs to run. That's for Monte Carlo, right? But there are organizations that invest very large amounts on GPU power.
But if you have a 40 terabyte database, you need a lot of GPUs.
Yeah, 40 terabytes is not what we. That's for Scream. Scream can take those workloads.
Let's make a small example, 10 terabyte database.
That we could look at.
And we have a GPU input table with 200 columns. And if you like to process such a table, you have to load every column into a different GPU.
No. It would be distributed. So each column will be distributed across all the GPUs.
Distributed around, because one GPU can store only 32.
No, it's not that having different column on different GPUs, but we have column distributed from region.
Yeah.
That's how it is distributed.
And you are using a compression algorithm for columns? Dictionary based or?
Yes, dictionary based definitely. Through other type compressions we have implemented compression speed compression, but for default use case we do not compress or double integers because, for example, because we have other tools like our visualization tools is able to prepare visualization like unmapped, so to double data in a certain region of the world, so to do a preculturation of metrics per pixel, and we can run with that, and to do that we can again access the memory with the data to prepare the render, and
Okay, I understand.
it has multi-side, we can just wrap a part of a column into further and use it. So
Okay, let's assume we have a 10 terabyte database and maybe 20 nodes. 20 nodes which like to process that database. They are equipped with 4 GPUs each. And how can they access the 10 terabyte must be shared between these nodes.
Correct.
And what do you use for sharing?
Distribution key. So that's been solved with MPP databases. So you take a key and you distribute on that key. So it might be customer ID, for instance.
The data must be transferred around a interconnection.
Depends on the query.
So for example, if you want to do simple aggregation or prepare visualization for aggregation with some warehouses, we don't need it because we have just our other parallels, and we can do a start computation lower
So the distinction about row orientated and column orientated. Column orientated was very popular with spinning media because of reading the way data was read and seek times. But with SSDs and NVMe, random access is almost as quick as serial access. So storing data on a disk in a columnar format doesn't really matter. You can do it on row-based or columnar. But I think what's important is we're focusing on what happens on the GPUs to get the best performance out of them. We are columnar because we're an analytic database. Like Jakob said, once that data is on GPU, there is a mechanism to drop it to disk and reload it very quickly, as fast as it'll go over the NVMe link. So that, the NVLink, which is 280 gig a second per server. So once you've got 3 servers, you've got close to a terabyte per second for data loading. So I think we're talking a lot about Scream, which is a different solution. Oh no, but we've talked about it quite a bit now. Yeah, they can help you out, answer those questions. Is there anybody out? I saw there was some other questions. Oh, okay. We don't support transactional workloads, so very much analytic workloads, load and then read basically.
Maybe just another quick one to understand the mathematics. The first line, the third line is 4 times slower, but it is running on 8 GPUs, and the top one is running on 20 GPUs, right?
Yeah, so if you look at so you could run this. Our software is on AWS, and if you did exactly, we actually, there was a Twitter engagement between MapD and Brytlyt when that was announced. They made exactly the same point, and we did say we have run on AWS, and if you want to do the similar benchmark using the same AWS hardware, which we've got in the second line there, that's AWS. You're welcome to do that. They didn't take up that opportunity. I imagine that's because
I just need to understand the mathematics, because you are supposed to be 40 times faster.
not than MapD. MapD is a very fast database. They're also a GPU database. So we're about four times faster than MapD. Yeah. So performance-wise, pretty comparable. They happen to be also the only one that's focused on GPU acceleration, where the other vendors are looking at different solutions. We've discussed our Scream is very much able to take on large workloads that rely on disk as well. But when you look at the dedicated GPU databases, Brytlyt and MapD are really the only ones that have that kind of capability. And the differentiator between us, we don't just think about performance. We think about how usable the platform is, the tool sets that really empower it. So performance is one thing, but without an effective tool chain with SQL, Postgres, stored procedures, user-defined functions, and all the PyTorch tool chain, you don't get to be able to use that performance. With Brytlyt, you absolutely can. No, we haven't been able to. That's quite a difficult one to get. Hannah will say that. If you speak to Exasol, they've got some very interesting TPCH benchmarks. They're also in memory, and they're probably faster than Hannah. Yeah, KDB I think is in memory. Spark. This Spark was in memory. That's an in-memory, all in memory. Yep. Thanks very much.